and I'm Director of Studies for Chemistry here at St John's, and I'm going to tell you a bit about what happens in the first year. So first year chemistry is the most popular first year subject. It's taken by about 75% of all students. So that means there's a big mix of biological and physical natural sciences students studying it. And this means that we have to take into account the fact that many of the bio-Natskis might not have either A-level physics or in some cases A-level maths. And we choose the way that we teach to take this into account. So we split the year up into 6 different areas. These will be things that you're probably familiar with from studying chemistry at A-level, but we try to do it with more rigor and accuracy. So the first thing that we look at is spectroscopy, and we focus on infrared and nuclear magnetic resonance spectroscopy. And again, you may be familiar with these from your A-level chemistry, but we try to get more information out of the spectra so that we can predict the structures of molecules with greater accuracy. The quantum mechanical treatment of the physical properties underlying these types of spectroscopy are a subject that needs to wait for later years. You'll see here I've got a couple of examples of how we can use on the left-hand side infrared spectroscopy and on the right-hand side NMR to determine the structures of molecules. So this gives us a good idea of the level of accuracy that we're looking at. So in the left-hand molecule, we've got 3 different carbonyl groups. And by thinking about the way that the bonding in the molecule might affect the strength of the CO bond, we're able to distinguish between, you see here, a carboxylic acid, an amide, and an ester. The second topic that we study underlies the way that we're going to treat both organic and inorganic chemistry later on, and this is using atomic orbitals to generate molecular orbitals that describe the bonding in the molecule with far greater accuracy and predictive power than anything you will have come across before. So we take atomic orbital wave functions, and don't worry, the level of maths in this is relatively trivial, and we do this to a large extent in a pictorial way, in the way that you can see here, and we generate an energy level diagram to explain where electrons are going to sit with lowest energy in a molecule. This allows us to understand or predict an enormous range of things about molecules that we come across in everyday chemistry. Following on from that, we start looking at organic chemistry, and straight away we use this molecular orbital approach to understand, for example, where the highest energy electron pair is going to be in a nucleophile, or where an electrophile is going to be attacked, by working out where the lowest energy unoccupied orbital would be. And so you can see that in the top left-hand corner here for various nucleophilic attacks. We combine that with this curly arrow approach to understanding organic reaction mechanisms that you may have seen in school, to be able to work out what's going to go on in some relatively complicated reactions. Now we come to a more analytical part of the course, so we're going to look at energetics, a little bit of statistical thermodynamics, which is something that will be covered in far greater detail in later years, but mostly classical thermodynamics that comes out of 18th century attempts to understand the processes underlying steam engines. And we'll investigate in more detail some concepts that you're familiar with from school, maybe like Gibbs free energy and enthalpy and entropy. And again, predict what types of reactions will be thermodynamically favorable on this basis. We'll also look at reaction kinetics. So how we can predict the types of rate laws that you see on the right hand side of the screen here from thinking about the relative rates of reactions of different steps in a multi-step process. So here we've got a two-step process, and obviously either the first step or the second step can have the largest activation barrier, and depending on which this is, we'll get different rate laws. So by actually doing these experiments and varying various different concentrations, we're able to see which is the correct rate law and therefore work backwards to understand what the mechanism of the reaction is actually like. And the final thing that we're going to do is look at inorganic chemistry. So we're going to look at the chemistry of the entire periodic table and try and come up with some predictive tools. So we're going to use molecular orbital theory again, but there may be cases where the molecules are too complicated to treat with molecular orbital theory. So we're going to use some other fundamental quantities to help us understand stability of molecules. So here we've got an example of how we can predict the stability of molecules by considering the electronegativity of the elements involved. So electronegativity here is represented by the Greek letter chi, that's that curly X. And on the x-axis, we've got the difference in electronegativity between our elements, and on the y-axis, we've got the sum of the electronegativity. And we can see that depending on the relationship between these two treatments of electronegativity, we can predict that some compounds will be metallic, some will be ionic, and some will be covalent. And then we'll look at different ways of describing the bonding.